Can you hear me?
Yeah, I can hear you.
I can speak louder or softer. What should be the? No.
I actually
Testing 1, 2, 3.
I think it's pretty good.
Once upon the time.
It's good.
Okay.
So I'll just
So, hello everyone. Hi. My name is Paulo, and just to give you a small introduction who I am, I'm a principal software engineer at Red Hat. I am one of the core developers of the Eclipse Vertex project, and I'm a polyglot, and I can speak many languages like Java, JavaScript, Portuguese, English, a bit of Dutch. And my my background started as well, I studied computer science, then I joined a couple of game developer companies because, yeah, you know, everyone wants to play in video games. And then you grew up. I started working as an architect, and now I'm working mostly on open source. But talk is not about me. The talk is about sorry, Vertex and a bit of chaos engineering. Just to put things a bit in perspective, if I have to make like what's the agenda of the talk, I would say that this Latin expression explains pretty much what's all about, like rare humanum est, or in English, to err is human. So we know that software is written by humans, humans make mistakes, so things will go wrong. And they have gone wrong several times, really badly. Like in 1987, and I look here because I need to look my notes, like on October 1987 was called the Black Monday. And the Black Monday happened because someone was investigating some inside trading, which is illegal, and investors got a tip that some company was being investigated, and they knew that if something would be found, the stocks would lose all their value. So what does a good investor do? Sell, 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 sell. And what happens when you do sell, 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 sell? You create lots of messages being pushed into the Wall Street software. And once that happens, you just DDoS yourself. The old systems went down for several days, and they lost 22.6% of the value, which means they lost around 500 billion per day, and this thing was done for several days. So lots of money was lost, lots of people got annoyed. Just to put it nicely, in 1993 there was like a big innovation, like the Pentium CPU came out. Before we had like the 86 series, like a 486, 386, 286, I'm going backwards of course, and then came out the Pentium. But the Pentium had an issue. When you divide a couple of floating point numbers, some of times it would give you like a rounding error, and the reason was because someone at Intel forgot to verify the division tables and forgot to add 20 of them. So that cost Intel $475 million. Well, in 1999, it's not really a bug, it's like a market opportunity, if you want to see it that way, because we were like being Scrooge, like in a Christmas Carol, saving space, only 2 characters for the year. And then now we have 2000, so what does 00 mean? Does it mean 1900 or does it mean 2000? So that cost lots of money because lots of software was rewritten. But you know, like it's not really like a big loss because all that thing was transformed into opportunity. So 500 million changed hands. And this year, last year, not exactly, I don't know exactly the dates, like we have like the meltdown spectra again, CPUs have defects, so we have no idea how much this costs. So what I want to say is that things will go wrong. If you use Windows, you probably know this screen. So because of this, some people start thinking, how can we try to make things go less wrong, because there's no really a way to make things not go wrong at all. So some guys at Netflix, which have a very popular service, as you might know, start observing that we need to study what can make things go wrong, because if Netflix is down, we don't get our series, then we get cranky, and then the whole internet is full of hate messages on Twitter and Facebook on how Netflix sucks. So they start thinking into this, and I start thinking, okay, let's make a definition. So what is chaos engineering? Chaos engineering is a discipline of experimenting on a distributed system in order to build confidence in the system's capability to withstand turbulent conditions. And I highlighted here like the most important parts, because important thing is that for Netflix they have so many systems, so they need to experiment on their distributed systems, and by doing these tests they have confidence that their systems will be able to withstand any problems. And finally, they do it in production. And I put this in bold because it's a very important statement. So this might look a bit countersensus, but it's quite important to know, because you have like development, pre-prod, and then you go live, and things go different. They don't behave the same. So in order to explain welcome. In order to explain a bit of chaos engineering, I decided to create a PaaS application. And because, as I said, my background started as a bit of a game developer, I decided to make a Pong as a service. So I will now talk a bit about this example. And if I wouldn't explain what my application is about, is Pong as a service is a highly available AI, because everyone likes AI these days, right? AI or machine learning. So I put AI, it's going to be great. Based Pong application that computes in real time the computer move using a web service that scales to any number of users. Sounds fancy. So once I started looking on Google for a couple of keywords like responsive, resilient, and elastic, you see like the top hit is like the Reactive Manifesto, and I think everyone has seen this before. You scroll, and if you haven't read it, it applies to reactive systems, and it defines 4 pillars, and then you see this picture. I bet everyone has seen this before. So this means that using message-driven architecture, your application will be elastic and resilient. So because of all these things, it will bring a value that your application will be responsive to the end user. So if I now have to build something, and as I said, I'm a core developer of Vertex, of course I will be using Vertex. So let me just give you a small introduction what Vertex is. So Vertex is reactive, as in reactive systems. That means like the image before, but I will show you a bit with a live demo. This means that you can build elastic and responsive, elastic and resilient applications. It is polyglot, so it runs on JVM, but it doesn't really require you to code in Java. You can use Java, Kotlin, or JavaScript if you're really into it. Because there are crazy people out there. It's distributed, so it means that it has a built-in peer-to-peer cluster manager that will define all the nodes on the network and automatically create a distributed network with itself, so you can share the load. So it's so it implements like a message-driven architecture, of course, and we try to make some effort to explain that it's a framework, and by making the point it's a framework, it means we're trying to say, well, we tell you how you can use it to build your application, but you have all the freedom to decide how your application behaves. So it doesn't force you like if you want to do a REST API, you need to do it this way. No, you are over control, because in the end, it's just a jar file. So it's a jar file that you add to your other jars that you already have in your application. So you can mix it with other tools or what you think it's the best to solve your problem. So if I have to put it like in diagrams, and this is pretty bad because the background is black. But what I want to say is that the Vertex implements the Reactor pattern. This is nothing really innovative, so to say, because if you ever work with a video game, you know this. If you ever heard or read anything about Node.js, you've seen something like this. So this Reactor pattern is nothing else than a forever loop, a while true loop, that keeps going in circles. And what it does is like, are there any events that need to be processed? And these events can be HTTP requests, file system access, gRPC messages to be sent or received, emails to be sent or received. And once there is a message, what the event loop does is looks up which piece of your user code is expecting that event, and then delivers it to your application. Your application does something with this event. So for example, you received an HTTP request, it's delivered on a handler or callback if you are familiar with Node.js. And what happens is that you do something with it. And once you do something with this request, for example, extract a couple of parameters, you can say, well, now I need to go to the database. So what you do is that you don't go on the database by yourself. You generate a new event and you give it to the event loop, and the event loop will then look up, okay, this piece of code knows how to go to the database, and it gets the data. Once the data comes back here, it looks up and it goes back to your code, and then you continue or you finish. So in a way, most people look at, oh, Vertex is like Node, but I like to add like this bottom aspect that it's different. And one of the differences is that, and again the background doesn't really help much, is that we have the multi-reactor pattern. And this means that unlike Node.js, where there is like one process, one single event loop, we will have one event loop per CPU core, which means that all your CPU capacity will be used with your application. So for example, this laptop is kind of a bit old for today's standards, has only 2 real cores. So if I would run a Node.js application here, it would only use 1. But if I would run a Vertex application, it will use the 2 cores. So everything Vertex will allow you to maximize your application to use all the resources available. On top of that, we have this thing called Eventbus, and this Eventbus is a very simple concept. Basically, it's a bus where you can send the messages like you saw before in those diagrams, the little balls. And this Eventbus is so simple that allows us to send messages between 2 different processes, like 2 JVMs, for example. And because of the clustering, it also means that the JVMs running on different machines can send messages across the network to other nodes. And important thing to notice is that the event bus has nothing to do with TCP/IP, so it doesn't need to know the TCP address or the IP port of this specific JVM. Instead, the Vertex has this, as I said, this built-in peer-to-peer cluster manager that will know exactly if you say send message from machine to the address consumer, and the consumer, for example, is running on this JVM, the Vertex will know the mapping between the address consumer and this IP and this port and send the message there, and we process there. The protocol, we try to keep it like a case approach, keep it simple and stupid. It's just a pure JSON payload by default. It can be configured to be binary, so don't worry if you are working, say, with a protobuf, then you can use binary payloads. But by default, use JSON. So anything, even non-JVM nodes could join the event bus, because it's just if your language or your framework can open a TCP socket and write a JSON message, then that's all it takes. So And on top of this, we're fast. And it's not something that, it's not really a reason why you use it to choose a framework. But most of the times when you think of distributed systems, you think like message delivery, frameworks, message-driven architecture always has lots of penalties in latency because you need to do lots of hops to find where to deliver the message. So to give you an example, I have here like the Tech and Power website, and for example, if I scroll this, oh, I'm scrolling on my notes, not on the, here's the mouse. If I scroll this and I see that like Vertex is listed here on the rank number 11, and this is just a very simple benchmark, so just take it with a grain of salt because it doesn't mean much, but it's quite popular because Tech and Power compares 297 different frameworks. I did this, but I'm not saying it out of my head, I was looking at my notes. And then you can compare things like, are we talking about comparing frameworks written in Rust, C++ or Go, which are expected to be fast, or are you talking about Java or Kotlin, for example? And then you see, well, Vertex is, we marked it as Java, so rank 11. And just to put things in perspective, if I scroll to number 57, which is an interesting one, you'll see Node.js. So most of the times you see presentations about Node.js, people say Node is fast, but they never show numbers. Here we have numbers.
Where is Rails?
Sorry?
Where is Rails in that?
Rails?
Rails.
Rails. Oh, yeah, probably play there. Express. There's Express, like the Express.js. Oh, Sinatra. Spring is here, but well, that's expected because it's still Spring 4. So let's be honest here. With Spring 5, we expect it a bit to go up, but not to really to the top. Let's keep going. I don't know if Rails. It's on the list. It's truncated to 1, so it's 162. It's there. And Rails is a bit worse, but I don't think anyone is using Rails that much these days.
I have a question.
Yes.
Because it's not clear to me. I'm not familiar with this one. It's not clear to me what exactly they.
Well, the Tech and Power compares as 6 tests, and this is just one. But the other ones are more or less in the same lines of results. So there's one that we are number 1, and I. On purpose didn't choose that one because it would look like, oh, I'm showing off, but that's not the idea. There's 6 tests. One is like serving a plain text response, which is this one. Another one is serving an JSON response. And these tests are run with like several levels of concurrency, like 8 concurrent connections, 16, 32, 64, 256. And then it's like how many requests can you deliver per second. Like the 100% is like the best, and then it's all relative to the first one. Second one is the JSON. The third test is making a database query using a relational database on a separate server, so it's not co-located. So you have the penalty of going on network, and that's the one we are number 1. And the reason is because we have our own Postgres driver, where we improved it to support all the latest features of Postgres, which most drivers do not implement it because they still assume that most people are on Postgres 8. And Postgres 10 has support for stuff like pipelining, which means that if you want to make 10 SQL statements and there is no correlation between the statements, it means that I can send the 10 requests even before the response arrives. So I can just push them to the server, and Postgres will then handle it with pipelining, like in the right order, return the results. So by doing that, we still make the 10 queries, But then Postgres is smart and can return everything. If the responses are small, say that you're looking just for like one row, it can pack everything in one TCP packet and return the 10 responses in one go. And that's how we win. And that's a valid test. And now that we are number one, lots of people start looking at our code, see lots of people making questions, and lots of people are interested. So that's a good thing. We see now that some people are going in that direction. That's test number 3. Test number 4 is kind of the same as test number 3, but then it runs a loop of queries, but they are interrelated. So it forces you to serialize and wait for the response before the next one. Test number 5, it's a mix, so you need to do a select on a table, get some rows, and then render an HTML page using a template engine. So then you're really not really comparing the framework, unless the framework itself has some built-in templating engine. But in our case, we're just using Rocker. And the reason was because, like a couple of benchmarks before, it was the one that had the best results. And because we don't have any specific one, we just say, okay, we will use that one. So we have some good results. And test number 6 is, again, doing lots of inserts and updates. So then you need to battle with the logs of the database and make sure that you can roll back, that the application doesn't hang. So we need to kind of look into transactionality. So it doesn't tell you much, but it gives like an idea of basic stuff that we usually do on our application, like connect to database, get data, do updates, and then see how fast can it go. So as I said, I was going to do a demo. So I have here a couple of slides, and I'll show the code really next. So if I have to put my application in the slides, there are 2 important parts. First is like the AI part, of course, where there's like this magical AI with a couple of if statements, with just if, else if. So there's lots of artificial stuff going on there. So basically what I'm doing is that I'm saying that my application listens on a specific address of the Eventbus, which I just define as pong-as-a-service.ai, and this will allow me to connect to it from anywhere in my cluster. So again, I don't need to know IP, ports, whatever. And then it's just creating an impulse. So I know where my player, the ball is, I know where my pedal is, so I need to calculate where should I give the impulse of the pedal to move, either left or right. So it's like min 5, minus 5 or 5, and that the 5 is just the speed. This is all hard coded, but it's just to get the idea. And then I could do some monitoring of my application by saying, well, I create a router, and a router is just an object that lets me map HTTP requests to handlers. So I could say, like, I want to have some liveness probe. Like one application can my Kubernetes or my OpenShift cluster could just look into this and say, okay, my application is good, so I can use it to do like rolling releases or deployments. And then this is quite interesting. We have a component called sock.js bridge, and what it does, like sock.js is a JavaScript library that allows us to use WebSockets from browsers to connect to the server. And this bridge, what it does is that it extends the concepts of our Eventbus to sock.js. So the browser itself can register addresses, so you can send messages to the browser or from the browser to the cluster. So with this, you don't even need to know which node in your cluster is responsible for the AI part or some business part. You just, from your browser, just need to say, send a message to the address pass.ai. And this simplifies lots of your code.
So one question regarding that.
Sorry?
One question.
Mm-hmm.
You mean that here you share the bus, the bus of
Mm-hmm. The message bus, yeah.
and let's suppose UI,
Mm-hmm.
you share the same bus, okay?
You
share
can,
message.
yeah.
Okay.
So I don't have it on this example, but I had a presentation one time, last year at CodeMotion. What I did, I had like this React application, and I was using the React state. So I wasn't using a Redux store. I don't know if you're familiar with this, but instead of using a store on my React app, I was just using the Eventbus, and I could send messages. Every time I update the state on the application, it would send a message to some address, and this address would persist it. So if I would start an application on some other computer, a message would be asked from that specific address, and it would restore the state, and you get like exactly where you were. So you can do stuff like that.
I also demonstrated in my presentation. I also have
Okay. So I do this, and then I have a specific handler to serve static files, and I created an HTTP server, and this kind of completes the code. If you're paying attention, the trick is, in my slides I say 2 or 3, but I only had 2 slides of code, because the slide number 3 is like you need to, if you think of chaos engineering, you only need to think of a plan B. And a plan B could be that you have some hard-coded service that you can deploy in case things go wrong. But this is like up to your imagination. Everyone knows their own problems. So if I say like, okay, we need to go to production with our application. So we go live. So what I have here, I already have like the application up and running. So if I have to show like the code, as you can see, the first part of which I said, this is the, by the way, this is the full code of the application. It's like 75 lines, 76 lines. So if I do not consider the imports, this is like the first slide. So well, I get the ball, and then I do some impulse, and this is like the second part where I say configure my breach. I set up the address, and I start the server, and here I just put some logging, like the application is already started. So in order to demo a couple of features of reactive systems, what I have here is I can do Docker. Now like a demo gods need to help. So I have an application running in Docker Compose, and I don't know if you're familiar, but it's quite simple. No, I want to minimize it. Basically, I define 3 services. So basically, the chaos is just my application that that I just showed, just that main. And then I have a second service called Bear, and this Bear is just a JVM that is not doing anything, and you can see that like on the first service is bound to my host port 80, and the Bear is bound to the port 8080. So if I would go here and say this one as a control tab, and I do something like local host. That's I should type local host just like that. You see the amazing application, and that the Eventbus is receiving the messages and updating the computer. The computer is upstairs, and I kind of have a suck here with my mouse because I was trying to do this like touch. So important thing to notice, if I go to 8080, there's nothing there, because as I said, I have a JVM running that can potentially bind to this port. So the important thing I want to show here is that if I create a new tab, I can do stuff like ps minus ef or Java, grep, and I see that my my application is running with this speed, so I can do sudo kill -9 copy paste, and yes, and if I grab again, my application died. So if I swap back to the other tab, yeah, you see that my application died. And one of the important aspects of reactive systems is that they should be resilient, and if the demo gods are with me, like after some pre-configured timeout, the cluster will notice that the main service died, and this can, I think it's pre-configured to 30 seconds because I'm just using defaults. So you start seeing that the node is noticing, the cluster is observing that some service went down. You see some logs here like warning, like this server doesn't react. And I kept it like this so you could see the things happening, but probably in production you want to have like a very short timeout so things are fixed for you quickly. So a couple of heartbeats will happen, and after a bit, and I hope I'm not totally sure about
Paolo, did you kill the correct one?
yeah, I killed the core, the cows. So let me see, like the bear and the AI are alive. So what should happen in, if I can, I need to remove the full screen and I do this. What it's happening. What should happen is that the cluster will observe that, well, that cow's node died, and then after some timeout it will regroup and observe, well, we are only two members now, there's this one and that one, and I will redeploy myself, redeploy the application that died on the bare machine. So if I would go now to this machine on port 8080, the application would be like automatically redeployed for you. So this is interesting for ops, like when you don't have something like Kubernetes cluster or some stuff like this, because out of the box the application will kind of self-heal for you. And then you can probably put a load balancing in front of it, so we don't need to have different ports. So if you're using Kubernetes, this is all done for you. The other aspect of this reactive systems is that scaling should be elastic. So, for example, say that we are getting too many requests and our AI component doesn't cope with the load. So I have a second service which is pretty much just that section of code of the consuming of these messages. So if I observe that my application is taking too much load to scale, the only thing I need to do is where am I? So I need to go to plus. I can do docker compose scale AI to 4, And then if I would switch back to here, you see that my application is now running with a very a large cluster of 5 nodes, and because it's message-driven architecture, every time there's a request coming from a web browser, it will just run robin to one of the available nodes that can handle that message, so you automatically spread the load across your cluster. So in a way, this kind of gives you the ideas of gives you the idea what are the benefits of using a reactive system. So going back to theme, so what is reactive? It's reacting to what? And basically we can define 4 kind of things we need to react. Vertex reacts to events because it's event driven. It reacts to load, so it, as you saw, like it can scale horizontally when I can just add more nodes on my my application. It reacts to failures by respawning itself on different nodes, and of course, as a side effect, it reacts to users because the user can still use your application because you still have a responsive application, even in case that there's some load or failure. So it's still. So once you have all these 4 reactions, then it means that you are in a reactive system, that you are asynchronous. And this is very important because most of the times I talk about asynchronous, and this is a bit too bad because when we, and I say we, but I don't know your background, but when we Java developers think of asynchronicity, we think of the package Java concurrent, where we have like a couple of asynchronous constructors there, like the completion, the futures, and the completion stage, and completable future. But completable future and futures are always delegated on a thread pool, so asynchronous is not really about multi-threading. Asynchronous is about never blocking. Because if you never block, it means that your CPU is free to do work. If you are in a multi-thread environment and you block, your CPU is just waiting, it's just doing nothing. So you just wasting your resources. So if I go back to the theme of the talk about cows, like now that we know the benefits of reactive systems and we think of cows, the Netflix guys defined a couple of principles, and they have 5. So principle number 1 is that we need to build an hypothesis around the steady state behavior. We should vary real-world events on this steady state to check how it goes. Run experiments in production, because that's where things usually go wrong, because even if you have a copy of production, pre-prod or staging, they're never really the same, and it's not always easy to find stuff. And because you're doing lots of experiments, you need to automate and make these experiments run continuously and monitor, of course. And once you automate and monitor, and if things go wrong, the goal is to minimize the blast radius, so minimize the damage. So if I put this according to the example I just saw, if I think of Pong as a service is a reactive system, it shall be responsive, delivering a consistent quality of service. It will be resilient, so it stays responsive in the face of failure, and it will be elastic, so the system stays responsive under varying load. So those are my goals, and these are specifically mapped to match the reactive systems as I showed in the small demo. So if I need to now think of real-world events, I need to think of software bugs like the Wall Street market crash, DDoS like the Wall Street network outages, because, well, that's what you probably everyone knows about the fallacies of distributed systems. Like should never assume that the network never fails. The network will fail, and if the network doesn't fail, servers will crash. So these are kind of things you need to think what you want to test. And there are tools to help you with that. The top one was written by Netflix, and it's quite good. But my opinion is it's made to solve Netflix problems. It assumes that you have an application deployed on AWS across multiple regions, and then it starts killing and spawning nodes across all regions, and monitors the state. I never had such a big application, so I found a poor man version of the tool, which is called Pumbaa. So the tool from Netflix is called Cow's Monkey, and there was this guy that created a tool called Pumbaa, and Pumbaa was inspired by the Lion King movie. So if you know the movie, you know it's like a monkey there. And what it does, it works on Docker containers. So this is great because nowadays everyone is Docker or Kubernetes. Kubernetes is Docker underneath. So it's really easy to use it to test. So I have a couple of examples after. So other tools would be Worker, which is like a load testing tool, which is perfect to DDoS yourself. So nothing better than load testing like without borders, like no control, to try to see if your application holds it. And to simulate network outages, there's another tool called IPRoot, which comes with Linux kernel. But this one you don't really to worry much about it because Pumbaa knows how to use it, so it can do all the work for you behind the scenes. So if I would need to test how to DDoS myself, I could use like Worker like this, and this means like Worker use 4 threads with 400 concurrent connections, because it's an asynchronous framework. It can do 400 connections per thread, and my laptop has 2 cores and 2 virtual cores, so 4 threads are okay. And for 60 seconds, just try to attack my server and see how it behaves. And by the way, this is the tool used by Tech Empower to come up who can handle more requests per second. If I need to talk about network outages, then I can use Pumbaa, and Pumbaa has lots of features. I have here a couple of examples. So basically here I'm saying Pumbaa using the net emulation layer for 1 minute, and this is because I don't want to be bothered installing IP route on my machine, because either I'm not on Linux or either because it's really complicated to get the right versions working properly. Use a Docker container that has this name on the Docker Hub, and what it's gonna do, like introduce packet loss for every 20 packets, start to correlate messages between them, and all containers that match this regular expression will be affected. And then you see that some errors coming up, and this is quite an interesting test. For example, if you're working with JSON, you will see that, and plain HTTP, not HTTPS, because of the plain text nature of it, you'll see that you start getting corrupt JSON. And sometimes the corrupt JSON is still valid JSON. So you cannot assume just because it passes the parsing and it's valid. And then you see like that your application gets like corrupted data on the database, and then you need to look, oh, actually probably I should validate the content, not assume that just because it's a number and instead of 1 I receive 10, which is still a number, it's correct. Other thing is like introduce latency, which is also interesting if you're probably working with mobile apps, because we can never assume that mobile network is fast. So here I'm saying like for 1 minute, randomly introduce a delay of 500 milliseconds between TCP packets, again on all containers that match that regular expression. And you can even do more crazy stuff like introduce jitter and correlation between messages, so messages get out of order and repeated. And so this is like really, if you are working with binary protocols that you expect to receive lots of messages, then you see that this will be a good test. And a good test for this is if you think of HTTP2 or gRPC, which is built on top of HTTP2, that you see like messages get all messed up. So there will be lots of TCP retries because the order of the message is messed up. So you see that the TCP stack starts increasing, and then it's not your application that will crash, it will be the container, because the stack is way too much. So you need to think of those things. And finally, we can simulate server crashes like Pumbaa can just say, you can just say randomly within 1 minute kill with the specific signal. You can specify, but this is like -9. Kill any container that matches this regular expression. So it's also good to test. And again, this works out of the box on Kubernetes and OpenShift. So once you cover this, of course, you need to automate, and this would be like another talk. Automation is a really complicated topic, but you know that we need to minimize blast radius, and it's the Murphy law. If things can go wrong, they will go wrong. So some tips that you can find online, or you can just think out of your head, like think of a fallback plan if you can. It's not always that easy. Avoid monoliths, because a monolith is a single point of failure. So if that one crashes, then you're in trouble. This is the tip from Netflix: deploy across regions or multiple platforms. Use circuit break patterns or Istio, because it's like popular right now. And then there's this blog called it's not a blog, it's like a GitHub page called Awesome Chaos Engineering, which has like hundreds of articles, books, tips, tools, everything. It's way more than I could cover in a presentation. And most important, you need to be creative. So I hope I haven't spoke too fast, because most of the times I do. So if you have any questions or anything, just feel free and ask me. And otherwise, you can see me on Twitter. You can check Vertex source code on GitHub and look at Reactive Manifesto on the principles of chaos engineering sites. And thank you. If there's any.
We can take a few questions. So if you do have some, then fire away.
Yes.
So if you have a system that, like in our case, what we face is that we have a Spring Boot application with a MongoDB behind that, and sometimes it's getting a lot of requests, and then it's pounding the MongoDB, which is then kind of stuck. Because it cannot process the data that he is observing. And then suddenly, at a certain moment, we see this that the stack gets full, like the number of TCP connections is full. And
yeah, they're all waiting. They're all queued.
They're all waiting, and at a certain moment, it doesn't react anymore. How would it then work if you would use Vertex as a kind of load offloader?
The bottleneck here, as you said, is MongoDB. So regardless of what front end you have, it will not really solve your problem. The difference would, are you using Spring Boot 2 or 1? 1. Okay, so Spring Boot 1, if I'm not mistaken, it's still like Spring 4. Yeah. So with Spring 4, it means that it's not reactive. It's a multi-thread paradigm. So it means for each request, it will spawn one thread. So threading as costs, I did a calculation one time. I don't have it here, but you can imagine, for example, that for each thread you need to allocate a couple of megabytes of memory and resources. So as MongoDB blocks and you start queuing, so imagine that you'll be out of memory soon because of all these requests, unless you put some throttling. And this throttling can be done either with systems that handle back pressure, like Istio, or in reactive systems, like even libraries like Rx, that allows you to say, okay, my current working queue is full, stop pushing me stuff, so no more connections are accepted. So with Vertex, because we are just one thread, it would mean that the time you would be out of resources is probably the moment you exhaust the operating system sockets, which by default is 64K. Unless you tweak it, then you can multiplex it. But until then, the solution, you need to put some queuing or some throttling.
That's basically also a kind of question is, can this function as a kind of queue out of the box?
No, Vertex doesn't do the queue. All the messages in between verticals, and verticals are like the small applications you can deploy in the same JVM. We can, most of our connectors, we support this back pressure feature, but that means that once a new request comes in, we say, okay, now hold on, you cannot do anything because I'm busy. Once I'm
you get a 503 or something.
it's well, it's kind of behaves like a circuit breaker. So until some moment, it allows you to hold the connection because it gives you like a time to let's see if the queue goes down and then continue. If it goes over the timeout, then okay, I'll need to stop and send the error back, and then it's up to the user. If it's HTTP 503, like a service unavailable or too busy. Yeah.
Cool.
You had a question?
I was curious what's your actual chaos setup in production, so how do you use chaos in your own application?
Well, I work for Red Hat, and because I work for Red Hat, I use OpenShift, which is like Kubernetes with some toppings to make it more fancy. And the examples I just gave, that's the ones I can use on my local OpenShift. Sadly, I had an issue with the laptop, and this laptop is too weak to run the cluster. But on a bit stronger laptop, I could just have like a mini shift installed, and then with PUM I could just see this behavior. And then, as I said, I would find all the interesting failures that I described, like gRPC message messed up, JSON corrupted and still being valid. And
I was curious just what you have in production, if you can share that. I don't know,
yeah.
if you can't.
I do, well, no, because I work with with customers, which it's not the open source part. I can talk about everything. The rest, no. I can give you the details of.
Just one quick question, because you mentioned Chaos Monkey from Netflix, so you said you wouldn't use it because it works with multiple regions. You don't need that, but can't you configure it to just work with one region? I'm not. I know the tool. I didn't use it.
I saw that it was really complex, so that really drove me off. And then I found this one, and I know that now they even have another one called Simian Army.
Yeah,
and Kong. So they have more, but to me it's like they are solving their problems, and they have really scalability and APIs that cannot take too much time to return. So. Not everyone. It's like when you go on these conferences and people say you are not Google. So that's why I'm not Google. I run my stuff on Docker. Pumbaa works great for me.
Cool.
No one.
One more last one.
I have seen that lately the Vertex has tried to go for some other VM like native builds. I don't know exactly what's the VM, but they are.
Oh, you're talking about the Graal VM.
Exactly. What the team has in mind with this, because I know that GVM can be a bottleneck in some kind of situations. At least if you know how the what the garbage collector can do with the code?
Well, GraalVM is a research project from Oracle that's been running for almost 10 years, and what they're doing is they have a JVM and they're dropping the J, so the Java part is gone, and now they say that they can run any language on it, and as a proof of concept they can run JavaScript, the latest ECMA standard, R, the statistical language, Python, and even binary code like C, C++ by delegating to LLVM to get the bitcode. So what they're doing is that they have this advanced compiler that can translate these sources to optimize the bytecode, Java bytecode. Well, I shouldn't say Java, to optimize bytecode. And they showed some results like their compiler, the generated code runs way faster than stock JDK. However, they're alpha. There are lots of bugs, there crashes. I've been working with it. I just add support for JavaScript to it. I can bootstrap a JavaScript application with Vertex both on Graal and JDK the same way. But I did found, and only today it got to work because they released the release candidate 2. Because until yesterday, they had lots of bugs that I reported lots of bugs and things like once you start the chaining methods and doing callbacks, which is popular in JavaScript, after like a level of 4, their compiler will just crash. So it's something to keep an eye on, but it's not ready for prime time. But they have this potential of making like small applications with small amounts of RAM and even translate it to a single binary like Go does. Like just have one binary that you can just deploy. You don't need to have like a container with a JDK. You just deploy the bare Docker container, which is like a few megabytes, plus your binary, which will be also a couple of megabytes, like that.
So what do you have in mind? At least
in a way it works. It behaves like a JDK 8. GraalVM is JDK 8, where the JIT has been replaced with their optimized JIT, and then they have this extension that allows it to run these languages on the side. So what we're doing, like we were already polyglot by nature, we're just trying to make sure that we run nicely there, because say that next year, 2 years from now, their bugs are gone and the people get more up. Their main user right now, I think, is Twitter, because they partnership with Oracle because they have some optimized Scala compiler that is way faster than the standard. I don't know if you ever work with Scala, like the compiler takes forever. So apparently with Graal they have some special compiler that is like instant and it generates even more optimized code. So Scala can be really, really fast. But then it's not the language itself, it's the runtime, because once you write same code in Java on Graal, it will also be faster. So.
Oh, nice.
Welcome.
Cool. Thank you very much.
Thank you.
We'll have one question to the audience, then we'll break for 5 or 10 minutes. There's some Coca-Cola in that fridge, so you can help yourself to that fridge. It's not mysterious. The biscuits are there for a reason. And there's also some pizza and a microwave. So, I think I'll give you guys a really easy question because I like you. Hand up.
1, 2, 3.
Not necessarily.
Yeah.
Yeah.
If it's like a socket.
We've got our second speaker now, Alexei. We have you talk about concurrency with Kotlin and Vertex. So it should be a nice, high quality talk. And yeah, please stay as interested as you have been. Ask lots of questions. It's really, really nice. So thank you.
Thank you. Hi everybody. My name is Alexei Soshin. I'm a software architect. I'm a big enthusiast of Vert.x and Kotlin. For about 2 years I've been working with them. Today I'm going to talk about pipelining. So most of the applications that we develop are usually something like this. We have a client, we have a web server, whether it's Spring or in Go, in Ruby, doesn't matter. We have a database, and most of the time what we do is just passing JSON around. So our client sends us some kind of JSON, we pass this JSON, probably map it into some active object or some POJO, or doesn't matter what you call it. You probably send it to database, fetch something from database, map it to JSON again, and so on and so forth. And it would take you about between 10 milliseconds if you run something quite fast, to 5 seconds if you're running on Ruby on Rails. So that's the usual application, but there are some applications which are different. So sometimes you may have an application without a client, maybe even without a database. It doesn't need a database, but it does a lot of stuff inside. So instead of just massaging some JSONs, it does some stuff, then more stuff, then even more, and so on. And the entire process may take like 10 minutes, maybe an hour, maybe 10 hours, I don't know. For that, we need pipeline processing. So for my example, we have a simple goal. Are there any cat lovers there? No? Okay. So we won't go with the lolcats. We will go with the example of comics lovers there. Still no? Okay. So I'm a comics lover, and I love comics, manga, and so on. And I get irritated that usual comics is like 20 pages, then you need the next chapter. And I really get irritated by that. So I would like to get the entire book, which may be like 4,000 chapters. And it's all images on my laptop. So what I will do is I pipeline the process. How does it look to download one page of comics or one page of manga, or maybe even an entire chapter, which is like 20 pages? Usually it's on some HTML, so you need to get this HTML, you parse it, you find the elements that are your actual pictures. You need to download each picture to your laptop, and then you write it inside some directory. And that's how you get 4,000 files on your laptop. So the naive approach is to use thread pool. So we are running a couple of threads, and each thread does all the work. So each thread fetches the HTML, then it parses it, then it finds the elements, then it fetches the actual images, then it writes it to a disk. So that would work. But the problem with that approach is that on this laptop I have like 4 or 8 CPUs, and in the meantime, while I have those threads, all the other pages are waiting. So if my threads are actually not that equal, and some of them may get stuck, and may get stuck even for longer periods of time. And that means that my entire pipeline is getting slower and slower, because if one thread got stuck, others are waiting, and that's like a snowball basically. And as you can see, the timings, which I actually, those are the real timings, are very different. So fetching the first page is like may get to 6 seconds. Then parsing the page is 70 milliseconds. Then actually finding the elements inside the DOM is like 7 milliseconds. And then there is you need to fetch the actual files, and it may take anywhere between 200 milliseconds to 6 seconds. It depends on your luck, it depends on the size of the image and so on. And then you need to write them to disk. And I remind you that the blue part is your thread, and that's what your thread is usually doing.
Quick question?
Yeah.
In this case, are the tasks not independent of each other?
Okay, so that's what we will rely on. Basically, those tasks, they are dependent on each other, because I'm fetching the HTML, which will hold the pages that I will parse, and I'm fetching the images. So I cannot fetch the content before I found what I need to fetch. So those steps are dependent on each other.
Okay. Because I thought we had 4,000 pages. They're each on a different page.
Yeah.
And just have a thread for each.
So it depends what you're trying to solve. Let's say that pages are actually metaphors, but you may have cases where you have either you fetch pages or you fetch chapters. So maybe this part of the fetch will be longer, or this part will be longer because maybe here you fetch like 20 pages. So it really depends on the use case. But if we look inside each box, so this box is like really big, 6 seconds. But if you look inside it, we don't do much inside. So we request the HTML. Then we have the network overhead, we have the latency, we have the timeouts, and so on. And after like 5 seconds, we get the results. And during that time, during that 3 or 5 seconds, other threads can do anything, because that's my thread pool. This thread had taken it's inside the thread pool. Others are just waiting. So other threads might get a bit annoyed by that slow thread. How can we solve that? So we can have pipelines with Vertex. So it's like a really big club sandwich. And instead of doing everything inside one thread, we will break the tasks based on how fast or how slow they are. So let's say if our fetching the HTML is slow, we will have a few workers for that, and workers in Vertex called verticals. So we will have like 4 of them, let's say. And then if my parsing is relatively fast, I can have 3 of them, and my finding the actual element inside the DOM is even faster, so I can have only 1 or 2. And again, the fetch content may be slower, so I have 3. And for the writing, for writing them on the disk, it's really fast, so I can have 1 or 2. And so I have, like Paulo mentioned, I have the elasticity. I can choose, instead of one thread that's doing everything, I can choose how many workers I have for each task. And I can even decide maybe to change them in runtime. I don't do it currently, but I can. Or I just can decide that next time I need to fetch something, I need like 10 workers to fetch my HTMLs and only 1 workers to do the write. Now, my goal is to change as few lines of code as possible and still get the most of my machine. So how do we do that with Vertex? Each task is vertical. So each of the boxes is a separate vertical. And as you can see, there can be more than 1 vertical that does the same. And all of them are communicating using the Eventbus. So if you're familiar, like let's imagine you would like to do something like that with Spring Boot, then you have the dependency injection. So you have your controller, and you have something inside it which will be probably your service, and have the dependency injection. Here you don't have that. You can send the message, and hopefully somebody will answer that message. And we'll see that in a second. And what's important to understand about that flow is that flow is non-linear. So if we have here a linear flow, 1 thread does everything. Here we don't know who will get this request next. So let's say the vertical number 4 gets to fetch the HTML. Then it throws some kind of message on the Eventbus. Then somebody else catches this message. So it's reactive and elastic. You send a message, you don't know who will answer it, and actually you don't care. That's the beauty of it. What's the advantages of that approach? First, and I'll try to demonstrate it if I'll have time, it's very scalable. The only way I can scale my previous solution with threads is to try and add more threads, but then I have either they will just get stuck and I won't improve anything, or I have a lot of context switches. Either way, it's bad for me. Here I have a constant number of threads, thanks to Vertex. It's concurrent, And it means that it can get a lot of job done, a lot of work done compared to the usual thread approach, because it doesn't have to wait. So if I fetch something, if I don't have to wait, I don't block the thread, somebody else will work a bit instead on my CPU. It's loosely coupled. So as I said, you throw a message and you don't know who will pick it up, and actually you don't care, so you don't need to change a lot of code if you have another step. And it's testable. And all those 4 points I'll show in my code. Before I dive into the code, there are also a few disadvantages to that approach. First, I don't, and I am actually not mentioning it here, but usually as a software developers, we're used to some concepts like we should have a MVC, we should have 3 layers and stuff like that. I'm as a software architect for sure see that a lot. And there are problems that you need, if you want to transfer something more than strings over this event bus over here, then you'll need to write a bit code. I'll show that piece of code. And you need to decide, and that's something that frameworks like Spring, which are more opinionated, solve for you. They give you a solution. Follow that way, and you will succeed. Vertex is not opinionated, so you'll need to think about how you decide to write your code. So let's go to the code. Who is here familiar with Kotlin? Okay, so I'll explain a bit. If it should be quite similar to Java and not very different, so I hope we won't get lost. So I don't, with Vertex, I don't need any container. It does everything for me. So I just have a main method. This is how main method looks like in Kotlin, a bit shorter. Fun is for function. So we create a Vertex instance. We do something that I'll explain later, which is registering a codec. And then we deploy our verticals. So as I said, we have different kinds of workers, and we have a different number of those workers. So here we define them. We define one content writer that will write the files to disk. We define 2 content fetchers, and so on and so on. So I can decide how many instances of each I want, and Vertex will deploy them for me. And now when I'm done deploying all the other workers, I deploy the main worker, which will start sending messages. So that's the manager, let's call it like that. And he will tell the others, okay, I know that I need to fetch now this manga. I'll start working. All the others are just waiting for work, they're idle. And when this guy starts, he tells the others what to do. So that's what we do. We send 900 messages over the event bus. So for the event bus, as Paulo showed, we need to tell 2 things. What's the address? And the actual message. So here I send just a URL, and somebody else needs to listen to me and fetch that URL for me. So I'm not doing anything here. Who's listening for this message is this guy. So I use constants to easily map the addresses. So I can go to this class and see what he does. So it's a vertical. It's just like a lightweight actor, and that starts spinning and listens to the event bus. So each time I send a new URL, this guy listens to it. It fetches the HTML of this URL. And then what it does, it sends the results, the raw data, to somebody else. So he doesn't do much. He just fetch the content and sends it to somebody else, and that's not to block. That's the main idea of those reactive and asynchronous systems. Now, a nice touch. A companion object in Kotlin is like static in Java. I have here two constants, and each vertical in the pipeline tells what kind of message it consumes and what kind of message it produces. So when I send something over the Eventbus, I send what I produce, and then I can check in the code who is listening to me. So let's say if that's what I'm producing, then I can say, okay, I'm as a HTML parser, I consume what HTML fetcher produces. So that's kind of nice way to sort your code instead of looking out for strings. So what we have here is HTML fetcher fetched us and some kind of HTML, just letters for us, and just a string. Then we consume that string, and we parse it. I use here a JSON library which receives a string and creates a DOM out of it. Then after we parse it, we try to do as the less work the better, and after we parse it, we send it again to somebody else. So that's a pipeline. Then we send it to attribute fetcher. Attribute fetcher only fetches us the links to the actual images, then to the content fetcher, which only fetches the actual images, and then to the content writer. And now, what's nice about this approach? I'll run the code. I hope the Wi-Fi here will hold. It's on my Wi-Fi, so it's okay. And here it starts. It already started fetching. And I also created a UI which uses WebSockets. It actually uses the Eventbus from JavaScript to Java that Paulo mentioned to update it in real time. So it doesn't do some kind of refreshes. It doesn't poll my server. It just gets pushes.
Just one more question.
Mm-hmm.
What will happen if you close now the screen and you open it again?
Okay, that's a good question. I don't remember how I implemented it. So let's see. Okay,
Okay.
So it gets again, because I accumulated the data, it pushes me again the new data.
Okay.
I saw a lot of retries. What does it mean?
Yeah, so that's the part of the reactive system. Now, basically, maybe I should stop soon. I'm basically DDoSing this poor server, and he's starting to reject my requests. So as a system, I'm elastic. That means that I fetched those URLs, and which is good. I managed to parse the HTMLs. Now I have a very big queue of files that I need to download. And the server is trying to block me, which is okay. But as a system, I'm trying to be as reactive as possible. That means that I'll show it in the code. And that's a beauty of Vert.x Eventbus. I try to fetch a file. If I don't manage to fetch it, if I get a timeout, what I do, I send again a message to myself.
Oh, itself, like the
Yeah, so I send a message to what I consume. So that means that if I got a timeout, I will retry in a few seconds.
There's an important aspect there, because it's not a function call. It goes back into the middle. It doesn't mean it means that your stack will not grow. So you never get
Yeah.
Stack Overflows.
So it's not recursive. Yeah.
It's an asynchronous recursive construct. How do you avoid them that it's going to be infinite?
Actually, it's not infinite. What happens is that it just it's like 900 chapters multiplied by 30 pages. It's just very large. It's not infinite. It will finish at some point of time because it does manage to fetch some of them each time. It just doesn't manage to fetch all of them. So that's the beauty. I use basically now my laptop is starts to get hotter because it uses all its resources, and that's a lot faster than what I used to do with threads. But what I need to do is a few things for that. So as I mentioned, there is this piece of code which says register codec. So it's just a fluent way to register to codecs. And what it means is that I can send a few basic objects over the Eventbus, which means strings, I think numbers, JSON's also supported. But if I need to send a DOM, which is a JSON DOM, Vertex doesn't know anything about that, I need to explain Vertex how to do that. So here, in this case, it's an OP, and I'll explain why it can be an OP. But if I would send it to another machine, I would say how I decode this object and how I encode it. But because all my verticals or my actors are running on the same machine, I don't need to do that. So I supply basically an empty codec, and it just will allow me to send those custom messages over the network. So for example, that's how Pojo looks in Kotlin. That's very nice. The language does all the getters and setters for you. But basically it means that I have I have a name and I have a buffer. So that's my custom object that I can send over the Eventbus, and the Vertex will know how to handle that, which is really nice. So we spoke about, okay, it's already 5,000 messages and counting, and only, oh, it's on my traffic, not nice. It's already a giga of my traffic. Soon I will get a call from T-Mobile. And what else I wanted to show you is that's all the code that I need to have WebSockets and have real-time updates. I have here the Eventbus. The Eventbus is connected to my server, and it just hears. It just listens for to the address called stats, and displays it in the DOM. And here what happens is that when I'm done writing a file to a disk, I write to the Eventbus. Now I don't even know who listens to it. Maybe it's another vertical, maybe it's on my machine, maybe it's on a totally different machine, maybe it's in JavaScript, maybe it's in Java, I don't know. I can still send it, and somebody will receive that, which is totally great. And the last part, so we discussed the scalability, we discussed the concurrency, the loose coupling. I don't have some kind of, I don't have 3 layers or 4 layers or 2 layers, something like that. And the last part is the testability. So let's look at the tests. all the code is tested, and the beauty of that approach is that each of the verticals acts as almost as a pure function. So you don't need to create all my ecosystem. I don't need all the fancy dependency injections. I only start the vertical that I test, and then I send it the message. So I don't start the entire pipeline. I only start the concrete vertical, and I send it the message. Then I listen to what it produces. So here I tell it, okay, do something with that, get me this HTML. And then in my test, I just wait until it responds, and I check the value. So that's a really nice approach, because it lets you test only what you need. So it's almost like a pure function. And here I don't run those tests much, but here I DDoS the Vert.x IO side a bit to check that I managed to parse the HTMLs. And yeah, that's a really nice speed. And yeah, that's all I wanted to demonstrate you. Any questions on that? Yeah.
How would you compare this approach with, say, for example, using an Apollo test component, completable future, for example?
Okay.
Pipelining of completable future, in this case, returning a string HTML, one service, the other function returning.
So basically, with computable futures, you still have the same thread pool behind it. So yeah, so it will be still more effective. What I even did, because it's not a Kotlin meetup, I don't demonstrate the same project that I written with Kotlin coroutines, which uses also like kind of completable futures, but still this approach is faster. Yeah. This approach really takes it to the limit. Yeah.
Yeah, because that's funny, because I was expecting, when reading the title, that you would explain the coroutines.
No, so.
But it's really cool to see.
Yeah, so as I said, here I use Kotlin mainly for brevity, because it lets.
Do you have numbers, like if you compare those?
No, I don't have numbers. I just when I originally wrote this example for the Kotlin talk, and then I rewrote it for Vertex, and I've seen that Vertex produces better results. At least I think it finished. Yeah, that's nice. So 10,000 images in about 10 minutes. Takes my phone Wi-Fi to the maximum. Okay, any other questions? Yeah.
Yeah, in the main file.
Yeah.
There you call a static function, I guess, the deploy verticals.
Okay, so.
I was just wondering, is that just finding all the verticals in your project?
So.
Oh, okay.
What it does, I tell how many verticals to deploy each time. So you can do that in two ways. One way is to deploy with a string. Then it will locate it by a class name. And another way is to deploy it by an instance. So here I don't need, in Kotlin, I don't need the keyword new. So I just create a new vertical, and it's already deployed for me.
And the number of instances, that is based on the time it takes to.
Yeah, that is based basically what I did. Yeah, as you see, I also take here the timings. My console is okay. What I did is okay, I have here a lot of retries, but I took the timings, and then I decided how many of each I need. So for example, here you see that I need 5 seconds to fetch the image, but only 1 millisecond to write it. So that's how I decided to how many instances of each I need. Okay, and yeah.
I have a question.
Yeah.
In general, in event-driven, In this case, I see that the event is mostly related to what you have to do next. So I would like to understand more or less what's the meaning of that address. If that address can be in some way, what the original meaning of that address is for this. So it is really the meaning of that address is to tell what you have to do next, or you can, for example, put in a general way saying maybe more event-driven.
Yeah, it's
saying this happened, for example, okay, and then someone will.
Okay, so that's a good point, because to get the statistics, I just publish the actual statistics. So here you can also have both. I didn't need that at this point, but what you could do actually is from each of your verticals you could publish a number of events. Like you could say, I parsed this file, do something, and also count the statistics. So what you would do, you would publish 2 different events from the same vertical, and then one event will get accumulated probably, and the other event will get pipelined further. Yeah.
Another question. How it works? So how you have the bus of event, okay, you have some event that are not processed, let's say. What will happen if I stop everything and then I go home? And I turn on the computer. What will happen with this event that I did not process or something?
Okay, maybe Paulo could. Yeah.
The messages are not persistent. When we were designing the Eventbus, we thought, okay, we need to keep it simple as possible. And if there are users who are interested in persistency, probably they use something like ActiveMQ. And in that case, we have a component that allows you to plug ActiveMQ kind of mapper. So every address that you specify there, what it will do, it will send that payload to ActiveMQ on that specific specific topic or queue, depends on the configuration.
Yeah, I can imagine you can provide the kind of way to perceive them, and then if you have a problem, you can reinsert the events when you start again, okay, or something like that.
Yes, but the default operation mode is like best effort.
Yeah,
if there's anyone listening, it's delivered. And it's guaranteed that it's delivered once. If there's no one listening, it's just discarded.
Yeah, okay.
But if we pull in something like ActiveMQ, then it goes into the queue until someone joins and says, oh, I'm listening on this, and then the ActiveMQ starts pulling from the queue and pushing to it.
Nice.
Yeah. And also, what I meant by loose coupling is that the effort to have another step, let's say that you need, I don't know, to rename your files, for example, is just adding another vertical and saying, now I'm listening, I'm consuming the event of the last vertical, and I'm producing something new. So you can always easily expand your pipeline, basically. Yeah.
What happens if you talking about the spinning up the first balls, if you make them all 10?
What do you mean?
10 first
okay. Actually, it wouldn't change much, because first of all, you have a limit of CPUs on your computer, so it won't speed up things much. It really depends on what they are doing. If you have a lot of network, for example, then maybe it makes sense to spin more of those, because they will anyway wait on the network, but you won't block. But you're trying also always to maximize what you have on your CPU. Any other questions? Okay, so to stay in touch, that's my GitHub, Stack Overflow, Medium, and so on. So I share these presentations. Thank you.